that what might be happening, and I'll show you the results that we have got. So first of all, I would like to mention this uncertainties that we have included, because the way we had calculated this height versus time graph, so the program itself has uncertainty of 0.001 second. However, here you can see it's uncertainty minute wise. So because this is our human error, we used our cursor, so we were not really sure that where we are putting it is right. So but however, this uncertainty, so our values are correct within this range of uncertainty. Okay. Now, okay, these are the data points that we have collected and plotted with time, right? So here, the question, what we have done is quadratic fit and cubic fit. The question must be asked that why are we interested in quadratic fit and cubic fit, right? We have tried to answer this question. I'm not sure if it is the right way, but this is what we have. This is our approach of doing the problem. So any function f of x can be expanded in polynomial of degree n. So what we have done is we have expanded h of t as polynomial of degree n. Right? Now we approximate this h of t as a3 t cube, a third degree polynomial. It's sort of a hit and trial. We try it, and then we approximately try to fit this particular curve with the experimental data that we have got. And this is the red one here shows that thing. Okay? So this red one here is the cubic curve, and points are the experimental data points that we have. We have tried to superimpose it. Then we impose another condition. We impose that a3 is equals to 0. What we obtain is a quadratic equation, and then we again try fitting this curve h of t, h2 of t, this function, on the same curve. So this here is on the represented in the black line, although it is overlapped, I think, so it's not really visible. Then and try fitting it with our experimental curve. So if the variation h1 of t, which is our cubic curve, and h2 of t, which is our quadratic curve, the mode of these two things is less than some value epsilon, where epsilon is a very small positive number, then our assumption that an minus 1 and so on up to a4 equals to 0 is valid up to a very good approximation. So this is true because our data follows this pattern. So therefore we can move ahead with our cubic approximation and deduce some results. So what are the conclusions that we have got from this? So number one conclusion is CME is accelerating. Now I'd like to go back to the graph. Okay. So here is this we can see clearly that as time increases, okay, oh, sorry, I missed a very important point here. I need to really emphasize that this is only true. So this, our assumption of cubic function or quadratic function or this polynomial, in fact, is true in the time domain that we have worked for. So we have worked for 10 hours of data points. We have not interpolated, neither interpolated nor extrapolated the data. So we are exclusively relying in this open interval 512 to 931. This is the time. So we are extensively working in this time domain only. Okay, yeah. So we are extensively working in this time zone. We do not know what might be happening, although we will make predictions, but our data is strictly between this time zone. Alright. So yes, so which gives us insight to CME, how long CME ejection process prevails. Now what I mean by this is, to understand what is happening in CME, and as I told, we have very little knowledge about the literature. I'll tell you how we imagine the model of what might be happening. So the simple analogy which our group took to understand what might be happening is gun firing a bullet. So what happens when bullet fires is, as soon as we fire the bullet, the velocity of the bullet pellet is 0, and then it after a delta t times assumes a constant velocity and it travels through space. Now if we are to fire that bullet in an empty space, in vacuum, then it will go with a constant velocity for infinity. But however, if we are firing that bullet in space where there is air, so the drag force will act and the velocity deceleration will happen, right? However, here we see that a coronal mass ejection, when it ejects out something from the surface of the sun, it accelerates, it's not deaccelerating. So I'd like to emphasize on this particular point here. What we have thought, I don't know, it might be wrong, it's quite possible, but what we have thought is It is about that particular instant where pellet has zero velocity and then it has some constant velocity. But in that time delta t, it from 0 to v, the velocity is changing and there is acceleration. So in that particular delta t, what our interpretation is that we are working in that delta t. So this 4 hours of time, which might seem too huge to us, but for sun, from sun's frame of reference, it might not be that huge, and that's why it's accelerating. And after some time, what might happen, since we do not have the data after 4 hours, what might happen is this CME will assume a constant velocity, and then it will deaccelerate because of the interplanetary drag forces if they exist. But we do not know that. The information we have is of 4 hours of data. Okay. So again, this entire data is collected for up to 10 solar radius. However, distance between Earth and Sun is 212 solar radius. So I cannot say what might happen beyond 10 solar radius. Okay. Now we can, to a very good approximation, find the speed of propagation of CME. So this thing is possible because we can write h of t in the quadratic form. And we have already discussed why I can do it, and again it is a very good approximation because the mod of h3 and h2 is less than some epsilon. We have, like, if we set the limit, then limit of error, then we can do this. So again, what this implies clearly is acceleration is which implies that acceleration is constant, which means we can use already known equations of motions. V is equals to u plus at. However, I would like to draw your attention to the fact that this is a very crude approximation because we are working from sun, and sun is rotating, so it is a non-inertial frame. So to use this equation from a non-inertial frame is already an oversimplification of the process that we have in mind, although we have not done how much impact it will have on those equations, but we do have that fact in back of our head that it is a non-inertial frame of reference. However, we can move ahead with knowing that we have this space for errors. So all you need to do is find acceleration. So if you have acceleration, you can get velocity as a function of time and displacement as a function of time. And that we can do from our velocity versus time graph. So A is equals to dv upon dt. And okay, so now again I would like to draw attention to the black lines here. Black curve. So here this black acceleration is constant and this is the value that we want to find out. What we have done is we have found this slope here. Right, so this slope is, so I have done calculations here. Yeah, V2 minus V1 upon T2 minus T1. So T2 minus T1 is 1 hour and V2 minus V1 is 60 plus or minus 5 kilometers per second. So that gives us acceleration of 1.66 plus or minus 0.14 into 10 raised to power minus 2 kilometers per second. This is the acceleration that we have found. Now, thus V is equals to U plus AT. Now we'll again impose a condition, initial boundary condition, let us say, at t equal to 0, be at 520. Then from the graph. So why we can do this is because this data is strictly, again, as I mentioned, it is between the regions. So we have to make again the assumption that since we are observing it in this time, so that for that we have taken into account, and we have set our t equal to 0 is at 520. So from graph, one can see what u is. It will be around 240 kilometers per second, and that is exactly here. And then v of t is 240 plus 80 is 240, and acceleration I have put in kilometer per second if we input time in second, right? So we'll try to, we can actually find using this equation what the velocity will be if I can use the board.
Advent acceleration.
Alright. So our equation says that v of t. So what we have found is quite amazing. That v of t is function of time. You give me what time you want, and I tell you what is the velocity of CME. So and also I can tell you what uncertainty we are working with. So if you give me any time t, I'll say okay, the CME speed must be between these two things, right? So we have 240 plus 1.6 into 10 power minus 2 into time in seconds, right? Now I'll not do the calculation. I've already done that. So, right. So at time when the time was 6:36, it has been already 84 minutes since our first we started observing CME, and 84 minutes implies 5040 seconds. right? So V of t would then be 240 plus, well, it will be something I am not written. The final value is from these calculations 323.664 kilometer per second, which from the available data it turns out.
6 hours 36 minutes.
Yeah, from the point of view when you started observing, it's a clock time. Okay, so clock started at probably 4 around. So yeah, this velocity matches with what the results have been found so far. So also on the basis of our assumption, it still in the uncertainty range and it is near the value of how CME propagates. So clear distinction in speeds between leading and trailing edges of the coronal mass ejection has been observed. Now this third point is implied by group 1 data. We do not have group 1 data, neither we have collaborated with them to really know the distinction between trailing and leading edge. So whatever my explanation is all about on the trailing edge. However, a distinction can be seen between the speeds of leading edge and trailing edge. So in summary, I'll end up that CME is accelerating. Number 2, we have found approximate speed of CME as a function of time, and thus speed at any time t can be calculated from our time domain. Now this our time domain is very important because we have not extrapolated or interpolated the data. We are strictly relying on our data. Clear distinction speed between, so this again is from group 1's presentation. No, it's not thank you yet. Yeah. So I would like to acknowledge all the hard work that has been done. Urvi is from BTech Astrophysics. She has shown a great leadership trying to talk with all the group members. We are in MSc, so she must have, so she has done a great job. We were awake, we were up late at night. Also, I would like to acknowledge so I am here, so it might be false. I don't want false credit. Rahi has done extremely good job in making PPT. I mean, it is all Rahi all over this. The whole presentation is Rahi. And Saraswati, Nandini was up with us. So everyone has done their part, and we are so happy to be able to be here and enjoy this winter school. For all the hospitality that we have received. Thank you so much.